Okay, we started section 7.4 last time, and we had taken a look at 3 different types of percent problems and how they can be structured. Hang on, where were they? These are our 3 different types, and we had done some examples of those. So that's where we left off last time, is having taken a look at those. So what we're going to do next is we're going to take a look at a few other things about percent. Example number 6 talks about using mental math. So mental math is really tricky. I think it's really important, but it's also hard to grade because if you're using mental math, you are supposed to be able to do it in your head. And that's really good. But I also want to know what's going on as you're thinking about it in your head. So it should be a process that allows you to do something in your head, but I want you to write down for me what it was that you thought about. Okay, so that's kind of what I'm going to model as we take a look at this. So the first example, and you're not going to do mental math on every problem. So it's also important maybe that I should mention that mental math does not mean approximation. It means we're doing the actual real problem. We're just not going to do it where we're writing a whole bunch of like multiplication steps down or whatever. Cora?
If it says mental math and you end up not doing it like mentally, is that okay? Or
So it's not okay because there will be a strategy that you can use to do it that way, which is what I'm trying to get at.
Gotcha,
There will always be one that you can use if it's asking you to use mental math. Yeah. Okay, so on this one, for example, 15% of 42. So one way to do it would be to set it up in proportion form, kind of like we've done the last few problems. I mean, that's one way to do it. That's not mental math, though. So mental math has to do with the fact that 15% is a really nice percent. And in particular, 15% can be broken down into 10% and 5%. And it is easy to do 10% of something. And we've talked briefly about that. We did it back in section 7.1, the early part of this chapter. But how do you find 10% of something? Yeah, you move the decimal over 1. So if we're dealing with the $42 and we're looking at the 10% part, we move the decimal place over 1. So the decimal right now is understood to be after the 42. And if I move it over, what do I get? 420. So think about, if I know 10%, how can I find out what 5% is? Somebody said it. Half it. Yeah, I just need to half it. So if 10% is 420, what is half of that? 210. And then what would I do in order to get what 15% is now that I have 10% and 5%? You add it together. And this would add together to be what? Yeah, it's 630. Okay, so make yourself the note to the side. This is something like this. 3 steps is the max that we're going to look at for mental math. What we just did was 3 steps. We found a 10% value, we found a 5% value, and we added them together. That is 3 steps. So if what you're doing takes you more than 3 steps, there's another way that we're expecting you to be able to do it that would work faster, shorter. And the real reason is that your brain doesn't really hold infinite amount of steps. You can't do that. I can't do that. And while you may be able to do 4 or 5 steps in your head, your students in your classroom aren't going to be able to do that. So our goal is not to try to figure out what's the capacity of your brain, all right? Our goal is to try to minimize the amount of things that we have to do to get to the right answer, okay? So the next one, 20%. Thinking about the last one that we did, how could I find 20% of $280? Yeah, I can do 10 and 10. And then I can add them the same way I did before. Or what else could I do? We could divide by 5. You're right. 20% is 1/5. So you could take the value and divide by 5. That's a good observation. Yeah. You could also do the 10% and then just double it, right? Instead of adding it to itself. So any of those would work for this. Let's do the 10% twice, and then let's actually do division by the 5 because that's not too bad for this one either because it's a nice 280. That works nicely on this one. So if I do 10%, what is 10% of 280? 28. And then if I add it to itself or I double it, either way, what do I get? 56. Okay, is that all right? If you think about the fact, like Candace mentioned, that 20% is equal to 1/5, which I'm glad you mentioned, we're going to use that in a different problem that's not 20% here in a moment, that idea. We can actually take the 280 and we can divide by 5. So how many 5s go into 28? 5. And I have a 3 left over, so it's 30. How many 5s go into 30? 6. So you could do that one that way too. How about C? 5% of 32. Already did a 5% one. What do we do? Yeah, we found 10% and then we halved it. So we found 10% and then we divided it by 2. So much like over here, I could find 10% and I could multiply it by 2. I can find 10% and divide it by 2 to get this one. What is 10% of 32? Yep, 320, and half of that would be what? One something. 160. Yeah. 160. Okay. So we shouldn't be seeing really any like elaborate multiplication with decimals or proportions set up when we're doing mental math. The last one is uniquely different, except that it's not, because Candace mentioned something earlier. Yep, Cora?
I had a really cool question about B.
Mm-hmm.
So with the division, is long division okay for mental math? Like if you were to write out the division problem or no?
If it's going to take that much work, it's probably not the idea either. Right. So 280 was really nice because the division for it wasn't complicated.
Right.
If it had said 282, that's a bit messier, and we would need to write something else out that probably doesn't end up looking like mental math at that point. Yeah. On D, we see 25%. And I always have students who want to find 10%, find another 10%, and then find 5%, and then add them all together. What's wrong, or what do you think I'm going to say is wrong? There are way more than 3 steps, right? We're at least at 4 or maybe 5 steps, depending on the processing that you did to get there. Your capacity to work through that many steps in your head, like legit in your head, is probably not realistic. And even if you can, which maybe you can, your 7th grade student can't, right? It's not going to work like that. So instead of doing it as 10%, 10%, and 5%, which we're not going to do it that way, if we think about it like the 20% idea where we did it as 1/5, that will work very nicely. So what is 25% as a fraction? Yeah, it's 1/4. So because it's the fraction 1/4, we're going to find 1/4 of 84, which is the same as taking 84 and dividing it by 4. And you can see, while I'm writing this like it's division, you don't really need to show any long division to divide this, right? It's even friendlier than the 280 divided by 5 that we did. So what is 84 divided by 4? Yeah, it's 21. So if you find yourself in a position where you're exceeding that 3 number of steps, 3 steps that are the ideal or fewer than that, pause and reconsider, is there another way I can do this that's easier? And it often does resort to fractions, and that works nicely, or to division of values if you think about it that way. Okay, we actually talked about this a little bit last time. I mentioned it in passing, but this is a formal problem asking the same question or a similar one. Why is it possible to have an increase of 150% in price, but not a decrease of 150% in price? Yeah, if we were looking at a decrease of 150% in price, this would be a negative price. And you might say, well, negative price, what would that mean? It would mean that they're paying you to take the item away. right? Can you imagine showing up at Walmart and them giving you money to take that bottle of laundry detergent? That'd be fantastic, right? No, it doesn't work like that, right? But can you have an increase 150% in price? Yes, it's called inflation, right? Yes. And taxes and all the things, and we've experienced it all very, very recently. All of us have. Yeah, so on this one, when we're doing the increase of 150% in price, you can always add cost. But there's only so much cost you can take away, and it's the 100% before it becomes negative, and that's a problem. And you could even argue, really can't take away 100% either, right? People don't give things away for free at the store. Maybe at a garage sale. They're just trying to clear it out, right? But not at the store. Is that all right? Okay, we're going to shift gears just a little bit to another topic within this section, still dealing with percents. And this has to do with interest. This is only going to deal with something called simple interest. So if you remember from like an algebra or algebra 2 course in high school where you were doing things with compound interest, we're not doing that in this section. And that's because that's algebra topics, and your certification is supposed to tap out at about 8th grade if you're doing an elementary certification. So that's why we're not covering the compound interest component. All right, so interest. Interest is the amount of money you pay or earn to borrow or lend money. Okay, so if you are borrowing the money, you pay interest. If you are loaning the money or investing the money, you earn interest. Principal is the original amount. That is the original amount you borrow or the original amount you let somebody else borrow from you or put at the bank to invest. The interest rate is the percent used to determine interest. The interest rate is always the letter R in the problem, and the R is as a decimal. So, for example, if you had 7% in decimal form, we turn that into the number 0.07. We move the decimal place, and that's our value for R. So you have to remember when you're working with the interest rate to turn it into its decimal form. Don't leave it as a percent. It's a very common mistake. The simple interest formula, there are two simple interest formulas. One of them is A equal P plus PRT, and the other one is A equal P1 plus RT. I've said there's two separate equations. They're the same equation. If you were to distribute the P through over here on the second listed equation, you would get the first equation. But sometimes it's friendlier to just pick up one of the versions to use it at a given point in time, but they're really the same equation. And the last one down here, interest, this is also simple interest, but the interest part itself, so this is simple interest. But this piece right here gives you the amount, the first equations that I just said gives you the amount after T years, whereas the simple interest right here gives the amount of just the interest that's accruing, right? The additional amount that you owe, right? So if you borrow $500, you're clearly going to have to pay the $500 back plus interest, right? So the first set of equations right here tell you how much you have to pay back, including the interest. This actually just tells you the amount of the interest itself. That's the difference. And you'll notice there's overlap between these, right? So this I equal PRT, it shows up right here in this equation. So this equation, the first one that's listed here, is really nice because it shows you you've got the principal. That's the amount you borrowed. I'm using borrow as an example. We could talk about investments, but I need to stick with one. So we're going to go with borrow. The P is the amount that you borrowed, and then PRT is the interest that you owe back, right? The luxury of buying something that you didn't have the money for right now. And then you can see over here, when we pull it out, it's written in a different form, a more compact form in some ways, but it's the same equation. All right, so we're going to look at a company. A company is expanding its line to include more products. To do so, it borrows $320,000 at 13.5% annual simple interest for a period of 18 months. I said it, but I didn't write it, so let me write it down over here. The t in these equations, any of the t's, it doesn't matter, is always in years. So you can see our first question gave us an amount of months. So the first thing we have to deal with, well, maybe not the first thing, but somewhere along the way, we have to deal with the fact that this number of months can't be used in our equation. I have to figure out how many years it corresponds to. All right, so they're borrowing it for 18 months. The question is, how much interest will the company be charged? It's only asking about the interest, right? So since it's only asking about the interest, which of these equations down here at the bottom am I going to want to use to just find the interest? The bottom one. The bottom one finds us only the interest, and that is only what I'm being asked in this problem. If you choose to use one of the earlier ones, that's fine. You can do that. It just means at the very end you have to take away the principal from it. It just means you're doing more work. So if you notice that it's only asking for interest, you'll be doing fewer steps. So it's I equal P R T. P is the principal. What is the principal of this particular problem? Yeah, it's the $320,000. R, the interest rate. What is that? Yeah, it's 13.5, and then we need to turn it into its decimal form. Corey, you just did that for me. Say it to me what it was. 0.135. So we want to make sure we take the rate, and then we turn it into its form as a decimal. That's 0.135. Remember, 2 decimal places to the left. And then my time is what? Yeah, it's 18 months, and then again, I need to turn it into its year form. That's 1.5 years. Okay, does that all make sense where all the pieces came from? Wonderful. At this point, it turns into an exercise for your calculator. So grab your calculator, let it multiply 320,000 times 0.135 times 1.5. Just be careful on the zeros that you get enough of them in there, and on the decimal place locations. This is a dollar amount when we're done, so we'll make sure we use a dollar symbol. What do you get?
6,800.
That's it, 64,800. Okay, did anybody's calculator not give them that value? Okay, great. The next problem is an interesting one, and I continue to like to use this problem because I was actually told in a not too distant past that something quite similar to this showed up on one of your certification tests, where it gave a question much like this in structure. So let's work through it so that you can see that it's not all that scary, but it's a little weird looking compared to the ones we've done. Because of a recession, the value of a new house depreciated 10% each year for 3 years in a row. Then, for the next 3 years, the economy began to recover. The value of the house increased by 10% per year. The question asks, did the value of the house increase or decrease after the 6 years? In order to answer that question, we have to do some calculations. But do you notice something that feels like it's missing in order to be able to do such calculations?
Number.
What number?
Like for the house.
Yeah, the value of the house is never given. Do you notice that? Okay, so the interesting thing is that we don't need it to do the problem. We can make one up. So we're going to make something up, and we're going to make something up that's going to be easy to work with. So the amount that we're going to use is $100,000 because it's easy to work with. Are you okay with that so far? You'll see at the end why it didn't matter. If you chose something besides 100,000 here, you're going to get the same answer I do at the end. And in fact, you'll even get the same answer for part B, where we look at the actual percent of the increase or decrease, okay? So we're going to start with assuming the value of the house is a $100,000 home. So the first year that the person has this property after year 1, it goes down in value by 10%. Now you can probably tell me what 10% of $100,000 is. What is it? It's $10,000. So it means that the house is now worth $90,000. I'd like to show it to you because the next step will be messier than this step in a slightly different way. Instead of talking about how much the value went down, how much of the value still remains? If we lost 10%, we maintained 90%, and 90% as a decimal is 0.9. So what is 100,000 times 0.9? You know it because you told me a minute ago. Yeah, it's $90,000. Now, after the next year, our value of our house, it's starting now at a $90,000 valued home, right? It's no longer worth $100,000. The market determines what something's worth. It's now worth $90,000. So at year 2, as we're going into year 2, the original price of the home is now $90,000. But again, I'm losing 10%, which means I'm retaining 90% of the price. So I don't lose $10,000 this year, right? Because $10,000 would make it $80,000. What happens when I do $90,000 times 0.9? I get 81. Why is it 81,000 instead of 80,000? Yeah, I have the same home, but the value of the home was 90,000. So the 90,000 times the 0.9 would be equivalent to saying, well, what's 10% of the 90,000? It's $9,000. So I don't lose $10,000 in year 2. I only lose $9,000 in year 2. We're going to do one more year of depreciation, year 3. So in year 3, I now am starting out with an $81,000 home. And this is the first place probably where the multiplication and the subtraction stuff, if we did it the other way, becomes messier. I still am going to have 90% of my home when I'm done, the value, right? So what is 90% or 0.9 times my 81,000? 72,900. Okay, so far so good? Okay, thankfully, in our scenario, after 3 years, the market takes a turn and it starts going back up, right? So unfortunately, though, our home is still only worth $72,900 3 years after we bought the home, and we hope that we don't have to sell the home right now or we just lose it, right? That's what happens. You just lose the value of the home. But at this point, assuming we're still in the home, it's going up 10%. So instead of it being worth 90%, what will it be worth? 110%. Right, we started at 100%, it lost 90%, lost 10%, that's why we got 90%. We're back at 100% and we're gaining 10%, so now it's 110%. What is 110% as a decimal? So we did 90% was 0.9. Yeah. 110% is 1.1. So we're going to take that 72,900 and we're going to multiply it by 1.1. What will you get? 80,190. That is better than the 72,900 that I was at, right? It is. We got a couple more years to do this. Year 5. So I've got 190. I'm still increasing by 10%, so times 1.1. What is the value of my house in year 5? 88,209. Okay, last year, year 6, I'm starting at 88,209. And I'm multiplying again by another 1.1. Where will that put me? 97,000. And let's go ahead and round to a whole number for the purposes of what we're doing. Houses, prices, it's whole number stuff. So yeah, $30 if we're rounding to a whole number. Okay, Our comparison is from the end to the beginning. Kaylee.
Where did the 110% come from?
It tells us that the value of the house, my screen, increased by 10%. So it's 10% more than what it was. It's 100%. So if you have your value of anything and you are looking at what you originally paid for it, you paid 100%. It's the original value, right? 100% means it's the original amount. The reason that we went up and down by 10% is because the problem gave us this depreciated by 10%. That means it goes down 10%, and increasing by 10%, which means it goes up 10%. So if we're taking our baseline as 100% and we're going down, we get 90. And if we go up, we get 110. Okay? All right, so compare my $100,000 house. It's now worth $97.30. Did it increase or decrease in price after 6 years?
Decrease.
It decreased. And did it really matter how much, according to this part of the question? No. I just compared where I started with where I ended, which means if you had started with a $150,000 house or, a house that was worth $1.5 million or something like that, all the same things would have happened. They would have been different numbers, but I still would have gotten a number at the end that was smaller than my number at the beginning. Okay? That's why, in this part of the problem, it doesn't matter what the price of the house is when I start. Is because my multiplication and my divisions, or I did multiplication everywhere, my multiplication steps, my 0.9s and my 1.1s all the way along, will still result in a smaller value at the end than what I started with. And you might say, well, what if it wants you to find the actual how much it changed by? Well, we can actually do that in Part B. Part B says, okay, but what percent did it actually change by? It doesn't say what dollar amount, because if I needed to know a dollar amount, I would have to know the exact value of the home. Otherwise, I wouldn't be able to answer that question. But to know the percentage amount, I don't need to know that. So let me show you how that works. So when we're looking at our at this question for Part B, we can actually set this up as a proportion like we were doing last class period. Right? The original amount of the house, that is the 100% amount, was $100,000. And we can figure out how much the value of the house went down. Well, it started at $100,000 and it went down to $97,030. So this numerator that I'm writing in right now is the loss. It's how much I lost on my house's value. Make sense? And I can figure out what percent that is as the missing piece in my proportion. What percent did I lose? Well, you can do the subtraction of the numerator, and if you do, what do you end up with? $2,970. Okay, there we go. Over my 100,000, x over 100, and I can cross multiply, right? Okay, so if I cross multiply, I have 2970, and then I've got two more zeros now. And I've got 100,000x on the right, or you can switch them, doesn't matter if it's right or left. So if I have my 297,000 divided by 100,000, what will I get? Yeah, 2.97. And that is a percent. That's what I'm finding because it was per 100 the way I set my problem up. And at this point right here, this 2.97, it will be 2.97 no matter what numbers you used on the previous slide. Because you eliminated your guesswork when you did the division and the subtraction. All our guesses, our choices for the values, all wash out to give you the same percentage at the end. Cool, right? Yeah, it is. All right, we have one more example, has 3 question pieces to it. So all the way during COVID, I took data. I still have my data in a massive spreadsheet. Actually, every single day in the state of Oklahoma, I wrote down data because I wanted to be able to use it in math problems. That's how cool I am, just so you know. So as of August 2020, the total number of positive cases that had been reported in the state of Oklahoma was 37,731. The population of the state of Oklahoma on July 1st, which is as close as I could get to the timing, so just bear with me on the fact that I know it's a month off, but just pretend that it matches up. On July 1st, we had 3,956,971 people in the state of Oklahoma. Okay? Everybody good so far? The question wants to know what percentage of Oklahomans had contracted COVID-19 as of August 1st. So we can set up this problem just like we did with our proportions and the percents. So we have something over 100, and that's what we're looking for. What percent is this? Well, it said there's 37,731 reported positive cases, and there's 3,956,971 people in the state. Yes?
How do you keep track of what goes on the proportions?
So the part that goes on bottom is supposed to match up with the 100%. So we're talking about a percentage of a population. So the total population is what's going on bottom because it's measuring the total, our larger number. And it's not always larger versus smaller, so I don't want to exactly say that, but it is the population that we're talking about at that point. So like if we were to do this caseload now, it's probably a higher numerator because there's more positive cases because people have tested positive multiple times and things like that. So it wouldn't necessarily show up with the larger number on bottom if we looked at the data right now. Yeah. Okay, we can cross multiply. So we have our 3,956,971 times x, and it's going to equal 3,773,100. And then we'll divide 3,956,971 on both sides. Okay, so we'll report to 2 decimal places. What do you get when you do this division?
95%.
Do you?
0.95.
0.95%. So the number that should be coming out of your calculator is 0.95. Did it do that? Yeah. So keep in mind, the way that we set this up is the value on top is the percent. We're not moving the decimal to find it, right? So 0.95%, it's really easy to look at and say 95. It's not 95. It's approximately 1. It's almost 1. Almost 1% of the population. Or we could say a mere 1% of the population at that point. It was very, very small as of August of 2020. Very small. Okay, when you flip to the next page, we're going to take a look at the children that are affected at that point. So we have 10.92 or 92% of the positive COVID-19 cases were in kids ages 0 to 17. How many kids does this reflect? So we had 10.92 is the percent out of 100. Whoop, out of 100. And the number of cases total that we had, like had been reported to this date, right, was the 37,731. So again, the 100% is the number of cases in this case, and we're trying to figure out how many of those cases were children. So we have our X on top. We can cross multiply. I don't have a lot of space on my screen. You've got more space on your slide, or paper, but not by much probably. 100x equals, and if we multiply these numbers together, it is 412022.52. And then what would we do? Yep, we divide by 100. So when we divide by 100, what will we get? And we got to round to a whole number because this is the number of people. There's no partial children running around.
4,000.
Yeah, 4,120. So it's 4,000 kids. So there was about 37,000, almost 38,000 people total who had contracted it in Oklahoma, and 4,000 of them were children, ages 0 to 17. Okay? All right, last question, taking a look at these percents. In Oklahoma at that point, at least pretty close to that point, July 1st, there were 981,328 kids. Okay? How many at that point then, what percentage at that point had actually tested positive for COVID? So we have this number of kids. We have this number of kids who actually had tested positive, and we're going to figure out what percent that is of our children. So this is much like the problem over here for the general population, but now it's the population of the children. So about 1% of the general population had tested positive. That doesn't mean it's 1% of the children, right? It wouldn't have to be, right? So if we take a look at this over there, and in particular, it probably wasn't, right? Even just realistically speaking, because there were different points throughout all of this where they were saying, don't go test, we're short on tests, right? Y'all remember that happening? They said, if you're feeling sick, just stay home. We don't have enough tests to test everybody. So it's not important if you're young and healthy to get tested. So even if there were positive cases, they might not have tested at that point. Those kind of things happened throughout. So we have our 4,120 cases of children at that point, and we have our 981,328 kids. And we have 100% of the population of children compared to our unknown X. So we'll cross multiply. I have 981,328 X equals 4120, and then a couple more zeros, 412,000. And we'll divide by the 981,328. Okay? What do you get when you divide that out?
142.
Yeah. It comes up very small again, right? And smaller than the 0.95, 0.42%. What does 0.42% mean? Well, I just want to give you some sort of perspective because these decimal values within percents feel funny, right? It's the reason we look at it and we want to say 42 because there's a decimal within it. This as a decimal actually would be 0.0042. That's what it would be. And if you think about the fraction stuff that we've done, it means 42 out of 10,000. So out of 10,000 children, 42 had COVID, or you could say approximately 4 out of every 1,000 if you want to think about it that way, a little bit smaller numbers to work with. It was very, very, very small. And we were making decisions as a population based on this set of numbers.